Time travel has been a staple of science fiction for decades, capturing the imagination of writers, filmmakers, and scientists alike. From H.G. Wells' The Time Machine to blockbuster movies like Back to the Future, the idea of journeying through time holds an undeniable allure. But is time travel really possible, or is it just a fantastical concept reserved for fiction? To understand the potential for time travel, we must first delve into the nature of time itself. According to Albert Einstein's theory of relativity, time is not a constant, unchanging entity, but rather a dimension that is intertwined with space, forming what we call space-time. In this framework, time can be affected by speed and gravity, leading to phenomena like time dilation, where time moves slower for an object in motion relative to a stationary observer. In this framework, time can be affected by speed and gravity, leading to phenomena like time dilation, where time moves slower for an object in motion relative to a stationary observer. One of the most well-known examples of time dilation is the twin paradox. Imagine one twin travels into space at near light speed, while the other remains on Earth. Upon the spacefaring twins' return, they would be younger than their Earth-bound sibling. This effect has been experimentally confirmed using atomic clocks on fast-moving aircraft and satellites, proving that time travel into the future is theoretically possible. Traveling to the past, however, presents a far greater challenge. One theoretical model for backward time travel involves wormholes, also known as Einstein-Rosen bridges. Wormholes are hypothetical tunnels through space-time that could, in theory, connect distant points in space and time. If a wormhole could be stabilized and manipulated, it might allow for travel to different points in time. However, creating and maintaining a wormhole would require exotic matter with negative energy density, a substance that has not yet been discovered or understood. Another concept for backward time travel is the use of cosmic strings, hypothetical one-dimensional defects in the fabric of space-time. By maneuvering two cosmic strings close to each other, it might be possible to create closed time-like curves, essentially loops in time that could allow for travel to the past. However, the existence of cosmic strings remains speculative, and the engineering challenges involved are immense. The idea of time travel also raises numerous paradoxes and logical conundrums. The most famous of these is the grandfather paradox, where a time traveler goes back in time and prevents their grandfather from meeting their grandmother, thus preventing the time traveler's own birth. This creates a contradiction. If the time traveler was never born, how could they have traveled back in time to alter the past? One potential resolution to these paradoxes is the many worlds interpretation of quantum mechanics. This theory suggests that every possible outcome of a quantum event actually occurs, each in a separate, parallel universe. According to this view, changing the past would create a new branch of the multiverse, leaving the original timeline unaffected. While this interpretation provides a way around the paradoxes, it also implies an ever-expanding number of parallel realities, each with its own version of history. Despite the theoretical possibilities, the practical implementation of time travel remains far beyond our current technological capabilities. The energy requirements, precision control of space-time, and the unknown properties of exotic matter all pose significant obstacles. Furthermore, any attempt to manipulate time on a macroscopic scale would likely encounter unforeseen consequences given our limited understanding of the fundamental nature of time. In recent years, physicists have explored the concept of chronology protection, a principle proposed by Stephen Hawking. This idea suggests that the laws of physics might inherently prevent time travel to the past, ensuring the consistency and stability of the timeline. If true, this would mean that time travel, at least to the past, is fundamentally impossible. In conclusion, while time travel to the future is supported by our current understanding of physics, traveling to the past remains speculative and fraught with paradoxes and practical challenges. The allure of time travel continues to inspire scientific inquiry and imaginative storytelling, pushing the boundaries of what we know about the universe. Whether we will ever unlock the secrets of time travel remains an open question, but the quest to understand time itself drives us to explore the deepest mysteries of the cosmos. For now, time travel remains a tantalizing possibility, a reminder of the infinite potential of human curiosity and ingenuity.